Today we're going to be talking about source transformations first. And to understand source transformations, we need to spend a moment and have a formal discussion on what it means for circuits to be electrically equivalent to each other. Okay. So we have been utilizing electrically equivalent circuits since the third or fourth day of class. Whether or not you guys realize that is an entirely different bag of cats, right? So let me explain exactly what I mean. We had a system where if we have some source voltage Vs connected to a network containing two resistors in series. Let's call these guys R1 and R2. If we measured the voltage drop across this network and the current flowing through this network, which I'm going to call IL, we could say that the following network is electrically equivalent, where this would just be that same voltage source Vs in series with a single resistance Req, whose value was simply R1 plus R2. The way we could verify the electrical equivalence of these two networks is to ensure that the same voltage drop appears across the terminals of the network, the same current flows into the terminals of the network, and therefore the same power would be absorbed by both of the networks. And we could do something similar to this for parallel resistances, for voltage sources in series, for current sources in parallel. Effectively, any case where we have been able to replace some combination of circuit elements with a single equivalent circuit element has been exploiting this concept of electrical equivalence. Okay. So what we're going to look at here in a moment is an electrical equivalence between two circuits that look fairly different from each other. Okay. So I'm going to introduce now what are called our practical sources. So on the left, I'm going to have a practical voltage source where I'm going to have some voltage Vs in series with some resistance Rs. And then across the terminals of this practical voltage source, I'm going to connect a load resistor. I'm doing the load resistance in blue to help us try to understand that this is something that we've added to this practical voltage source over on the left. And this will be our voltage drop across our load and our current flowing through our load that we are going to use to test for electrical equivalence here in a couple of minutes. Okay. So before I draw our practical current source, let me just go ahead and make a note of this thing. This will be our practical voltage source model. This is called a practical voltage source because it is a way of modeling real voltage sources like batteries and things like that, okay? So every other time that we've seen just a voltage source by itself, that was an ideal voltage source because it was able to provide literally any amount of current we could ever possibly need, okay? A real battery or DC source or something like that does not have that luxury. The amount of current that it can provide is limited by the internal source resistance labeled as RS. So the better we design a practical voltage source, the lower that RS value will be, meaning it will behave more and more like an ideal voltage source as that RS trends towards 0 ohms, okay? So to put this in context, how much current do you think can be supplied by a AA battery? Not a whole hell of a lot, honestly. At maximum, it would be a couple of amps of current, and then if you were able to supply a couple of amps of current with a AA battery, it would not last for very long, like literally less than a minute. For a car battery, it can probably produce several hundreds of amps for a short duration of time, but in the steady state, it's probably only pushing out a few amps to keep the lights on in your car and all of that kind of stuff. And it has the luxury of having an alternator constantly trying to supply it with power as well to keep it topped off. Okay, so this RS resistance here is modeling a real battery's ability to produce some fixed amount of current. Okay. On the flip side of things, we have a practical current source model as well. So in our practical current source, we would have an ideal current source IS connected in parallel to some source resistance RS. Bless you. And then across the terminals of this practical current source, I'm once again going to apply an identical load resistance RL. This is my voltage VL. Here's my current IL, like so. So if the role of the resistor in the practical voltage source was to limit current, the role of the resistor here in the practical current source is to limit the amount of voltage that we could see across our ideal current source in a particular system, right? So if I were to have an ideal current source that is open circuited, our circuit analysis rules tell us the only way that that happens is if the voltage drop across that guy is infinitely large. This resistor RS here constrains that voltage to be some finite number, okay? So this is our practical current source. And so what we're going to do here in just a moment is we're going to figure out if we can determine the conditions that are necessary for these two practical sources to be electrically equivalent to each other. Meaning that from the perspective of the load resistor, it wouldn't be able to tell if it was connected to a practical voltage source or a practical current source, meaning that we could use them interchangeably, okay? So in order to do this, I'm just going to calculate the quantity VL and IL for both the left-hand circuit and the right-hand circuit. So for our left-hand circuit, I'm going to find our load voltage VL using voltage division because I have a voltage source with two resistors in series. So my known voltage in this case is Vs, and my ratio of resistances is going to be RL in the numerator, since I'm finding the voltage drop across it, over RS plus RL. To find my load current IL, I'm just going to use Ohm's law. So that would be my total voltage Vs simply divided by a factor of RS plus RL. So before I move on from our analysis of the left-hand circuit, does anybody have any questions about where those results came from? All right. So now let's do the right-hand side, okay? So to find my voltage VL over here, I'm going to use Ohm's law. So the voltage drop VL will just be IS times the parallel combination of RS and RL. So that's going to look like IS times RS times RL over RS plus RL. And to find my current IL, I'm going to use current division. So that's going to be IS times 1 over RL over 1 over RS plus 1 over RL. And with a little bit of algebra, I'm not going to bother showing you guys. It is rather trivial. We could write this as IS times RS over RS plus RL. So my question to you all is, under what conditions are the voltages VL equal to each other? And under what conditions are the currents IL equal to each other? Correct. So that current division relationship becomes IS times RS over RS plus RL. So anybody have any thoughts yet? So if we set those two voltages VL equal to each other, I think we could pretty easily see that there is a common factor of RL over RS plus RL in both cases, right? So I have that guy right here in this resistance ratio. I have that same guy right here. So it looks like I would need VS equal to IS times RS for these guys to be electrically equivalent to each other. Let's check what's going on in the current, right? So down here, I have a denominator of RS plus RL, and I have a denominator of RS plus RL. So the numerators need to be equal to each other. And once again, we have VS would be equal to IS times RS. So our transformation here is simply that our source voltage Vs needs to be equal to Is times Rs, which is literally just Ohm's law. So as long as the source resistance is equal on our practical voltage source representation and our practical current source representation, I can transform between these two practical sources, okay? So let's look at your in-class assignment problem on the first page, and let's go over what the rules for this are. So how this is going to work is simply whenever we see the positive polarity terminal of a voltage source on top, when we convert it into a current source, it's going to have the arrow direction up. If we were to see the positive polarity terminal on bottom, our current source's arrow would be pointed down. If we saw our positive polarity terminal on the right, the arrow would be pointing to the right. If we saw the positive polarity terminal on the left, the arrow would be pointing to the left. Similarly, anytime we see a current source and we want to convert it into a voltage source, if the arrow is pointing up, the positive polarity terminal is on top, the arrow is pointing down, the positive polarity terminal is on bottom, and so on and so forth. Okay. So let's look at this guy in part A here, okay? So we have a 10-volt source in series with a 5 kilo ohm resistor. So my solution should be a current source. Since the positive polarity terminal is on top, the arrow will point up in parallel with a 5 kilo ohm resistor. The value of the source resistance literally never changes. So the only thing we'll have to do is figure out what size the current source should be. So what's 10 volts divided by 5 kilo ohms? 2 amps. You're off by a factor of 1,000. 2 milliamps. So this network is our transformation of that practical voltage source. Okay. So let's look at part B. I have a practical current source, so I know I'm going to wind up transforming this into a practical voltage source. So that'll be a voltage source in series with some resistance. Since the arrow is pointed down, the positive polarity terminal of my voltage source will be on bottom. My 8 ohm resistor is going to stay an 8 ohm resistor. So what should the value of that voltage source be in my practical voltage source representation? 2 amps times 8 ohms is 16 volts. Okay. So nothing wild or crazy there. For part C, we have a 3-volt source, positive polarity on bottom, in parallel with a 6 ohm resistor. So I want you guys to tell me what this is going to transform into. Current source, so what direction is the current source? Down, okay. In parallel with a 6 ohm resistor. What's the value of the current source? So I heard 2 amps, which I believe is incorrect. Half an amp, right? So V divided by R. So 3 over 6 is 1/2 of an amp. Okay. Lastly, what's going on with D here? So when I transform D, what am I going to get? 14 volts, positive polarity on top, in series with a 2 ohm resistor. Okay, so I think we largely understand the rules for how to apply a source transformation. So now let's look at this in context of how it might be useful to you all. So I'm going to draw a big growth circuit here. I'm going to define this voltage as Vx like so. And our ultimate goal in this particular circuit is to determine that voltage Vx. Now, I know 100% that we could solve this using nodal analysis or mesh analysis. But let's say that this were a test question, meaning that we would be constrained to 3-equation, 3 unknown systems, okay? So you didn't have a computer available to do a bunch of heavy lifting for you. How many meshes does this circuit have? So it has 4 meshes, and then we would have also a relationship for the voltage Vx. So that means that we would have a 5-equation, 5 unknown system to solve for, which is beyond the scope of what our calculators are capable of doing. How many nodes does this circuit have? 1, 2, 3, 4, 5, with an unknown quantity Vx as well. So it would also, if we count one of those nodes as ground, we would also have a 5-equation, 5 unknown system. Once again, our calculators couldn't easily do this without lots of substitutions. We'd probably wind up using a computer. With just a couple of source transformations, we can actually bring this thing down to a level that we could have solved it on the 3rd day of class. So how many practical current sources does this circuit presently have? 3. Why can't that thing at the top that is a current source in parallel with the 20 ohm resistor be treated as a practical current source as well? Who cares if it's dependent? It's still a current source in parallel with a resistor, which means it's a practical current source, okay? So we can transform that guy as well if we need to. So what I'm going to do is I'm just going to set up some terminals here, and I'm going to show you guys how I like to think about things, okay? So here's a set of red terminals. Everything to the left of this guy, of this set of red terminals, is a practical current source. Here's a set of purple terminals. Everything between these guys is also a practical current source. And then lastly, I've got another set of terminals over here, and everything to the right of these guys is a practical current source. So how I like to approach a problem like this is essentially I disconnect those networks at the terminals, transform them, and then plug them back into the circuit. So, for example, our 5 amp current source that is in parallel with a 10 ohm resistor might look like so here's our 5 amp current source in parallel with our 10 ohm resistor. I'm going to draw those red terminals so I know where to reconnect this guy. This is going to transform into what? A 50-volt source in series with a 10 ohm resistor. Let me scroll down here. I have a 20 ohm resistor in parallel with a 2Vx voltage source. So what would this transform into? What was that? 20 times 2Vx, yeah, so 40 Vx in series with a 20 ohm resistor. where the positive polarity terminal is on the right because the arrow of the current source is directed to the right. And then lastly, we have a 25 ohm resistor in parallel with a 1 amp source direction down. So what would this transform into? A 25 volt source in series with a 25 ohm resistor. And our voltage source will have positive polarity on bottom because the arrow was pointed down. So, I'm sorry, what? No, it was 25 up here. So it was still 25 here. When I transform it, that has to stay the same. The source resistance. Yep. So I am transforming everything to the right, which is the practical current source, into a practical voltage source. Carter, what's up?
Vx at the current source on 1 amp.
So if Vx were the voltage drop across the current source, I probably wouldn't want to transform that. So with a voltage, it tends to work out okay as long as you keep the voltage between the same nodes. So if the voltage Vx were the voltage drop across the 25 ohm resistor in parallel with the 1 amp source, it would be the voltage drop across the terminals of the practical voltage source. Whenever the controlling variable is a current, that kind of ruins everything. So I, generally speaking, tend to never transform the element that is controlling the controlling variable, because it's too easy to make a mistake and lose that information or misapply it elsewhere. Okay, so what I'm going to do now is I'm literally just going to erase all three of those practical current sources from my original diagram and replace them with the practical voltage sources that we came up with. Okay, so my 5 amps in parallel with 10 ohms is going to now look like 50 volts in series with 10 ohms. My 20 ohm resistor in parallel with a 2Vx current source is now going to look like a 40Vx voltage source in series with a 20 ohm resistor. This guy over here, I'm going to replace with my 25 ohm resistor in series with a 25 volt source direction down like so. So I've used source transformations to convert this circuit from something that had 5 equations, 5 unknowns using either nodal or mesh to literally a single loop circuit that we could have analyzed on the 3rd day of class. Okay, I can make this even more simple now by applying the resistor combination techniques that we learned in our 4th class meeting and the source combination techniques that we learned in our 5th class meeting, right? So I can see that I have 10 ohms in series with 10 ohms in series with 20 ohms in series with 25 ohms. Again, I'm leaving that 5 ohm resistor alone because that's where the voltage drop Vx occurs. So I'm just going to sneak this equivalent circuit down here. So 10 plus 10 is 20, plus 20 is 40, plus 25 is 65. So I would have a 65 ohm resistor. I'm going to leave my dependent source alone. Here's my 5 ohm resistor, across which I have the voltage source Vx. And then I have 50 volts in series with 25 volts. It's going to look like 75 volts. And that is my simplified representation of that circuit. So those two circuits are electrically equivalent to each other, because all I've done is resistor combinations, source combination, or source transformations, and source combinations, right? So I feel like analyzing that guy right there, which we really got to in 2 steps, is a lot easier than analyzing our original circuit was. So this can be a powerful tool, but things have to work out pretty perfectly, which was by design in this case for it to be super duper useful. Okay. What we're going to learn in Wednesday's class meeting is what's called Thevenin and Norton equivalent circuits. And it's a different way to get these exact same results that is broadly applicable to essentially everything. Okay. So once again, you're learning a quote unquote hard way, and then you learn the easier way. The easier way, Thevenin and Norton equivalent circuits, is actually much more difficult, but it's useful literally everywhere, which is why I prefer it. Okay. So anyway, we could, if we were so inclined, now solve this circuit pretty easily for Vx just using KVL and Ohm's law. Since hopefully we all have that down, we're going to move on to bigger and better things. Anybody have any questions about what we did here? All right, so now I want to talk about what's called the maximum power transfer theorem. We are going to derive these results using a practical voltage source representation. However, because we know how to convert from a practical voltage source to a practical current source, we can pretty easily get what the results from a practical current source perspective would be. Okay. So maximum power transfer theorem. So let's say that I had a system that I could simplify down to a practical voltage source connected to some arbitrary load resistance. Okay. So a system like this. Now, earlier in this lecture, when we looked at literally this exact circuit, I found the voltage across the load resistor using voltage division. Just to remind you, that came out to be Vs times RL over Rs plus RL. And our current, IL, was simply Vs divided by Rs plus RL. If I put these results together, I could say that the power absorbed by my load resistor is just going to be the product of these two quantities, VL times IL. And so that's going to look like Vs squared times RL over RS plus RL quantity squared. What I'm going to do is I'm going to plot my power as a function of my load resistance. Okay. So here's PL as a function of RL. And then here's RL. On this plot, I'm going to start from a load resistance of 0 ohms. So effectively, a short circuit. And I'm going to go all the way to my load resistance being infinity or an open circuit. So this graph is telling us what the power is going to look like for literally all possible values of what our load resistor could be. And it's going to wind up looking something like this. Where on the left-hand extreme with our load acting like a short circuit, we know that there should be no power absorbed because since there's no voltage drop across a short circuit, there can't be any power absorbed by a short circuit. And on the right-hand extreme where we are at an infinite resistance, we know that we should also once again have no power absorbed because if there's no current flowing through the load, then there can't be any power absorbed by the load either. Okay? So for most values of resistance, or actually, let me put it this way. For most powers that we can see from this graph, there's going to be two different values of resistor that will achieve that particular power level, except for the maximum. Maximum power occurs at one very specific resistor value, right? So if I were to plot here, so this is our maximum power. This is RL equal to question mark. And our ultimate goal here is to figure out what value of resistor in our load resistor position causes maximum power transfer to occur. Okay. So anybody have any thoughts on how we might sort that out? Yeah. So way back when I took math 241, 20 damn years ago or whatever it was, I learned that to find the maximum value of a function, we took the derivative of that function and set it equal to 0. That sound okay? So I have a function, PL. My variable in this case is RL, so I feel pretty strongly like I can just take the derivative of PL with respect to RL and set it equal to 0, and I'll find out which value of RL causes this thing to hit its maximum, okay? So the derivative of PL as a function of RL with respect to RL, okay? Now, I have a function of RL in the numerator and a function of RL in the denominator, so I believe I have to use the quotient rule to make this thing work, right? Quotient rule, if I'm remembering correctly, and correct me if I am not, is essentially the function, or excuse me, the derivative of the function in the denominator times the numerator. No, actually, it's the derivative of the top times the bottom minus the derivative of the bottom times the top over the bottom squared, right? So I'd have RS plus RL squared times the derivative of the numerator with respect to RL, which in this case is literally just going to be VS squared, plus the numerator VS squared RL times the derivative of the denominator, which is just going to be 2 times RS plus RL. I'm going to put my 2 out here, and I'm going to divide this by RS plus RL to the 4th power. So did I do that derivative correctly? What did I screw up?
So you change rule for RS plus RL squared.
Mm-hmm.
So you have to multiply by another RL. No, I'm wrong. You have to multiply by, but you're supposed to subtract the numerator.
Oh, that's right. It is supposed to be a subtraction there. You're absolutely right. But the derivatives were done correctly.
Yeah.
Yep.
I don't think you know after you actually transfer with the square root of it, that you experience with a RL, but that'd be if you actually squared it.
Yeah. All right. So since I'm trying to set this thing equal to 0, my numerator just needs to equal 0 in order for this whole thing to equal 0. In fact, it's pretty much impossible for my denominator to ever equal 0 if RS is a non-zero quantity, right? So I have RS plus RL squared times VS squared minus VS squared RL RS plus RL all times 2 is equal to 0. So let's see if there's anything that we can simplify really quickly. There's a common term of VS squared that can be gotten rid of, right? So if I divide both sides through by VS squared, 0 over VS squared is still 0, so that changes nothing. I can throw away that common term on the left. Now I'm going to need to FOIL this thing out, 8th grade math style. Excuse me. So to me, that's going to look like RS squared plus twice RS RL plus RL squared. And then I'm going to have minus. And let's see what's going to shake out over on this side. So I'm going to have a 2 RL RS. And then I'm going to have a 2 RL RL. So that's just going to look like 2 RL squared. And set this equal to 0. And now I believe I can see that this 2RSRL cancels this minus 2RSRL. And I'm going to have an RL squared minus 2RL squared. So this is going to simplify down to RS squared minus RL squared is equal to 0. So it seems to me like RS must be equal to RL in order for maximum power transfer to occur. So yes and no. Okay. Impedance matching is the AC version of this. So not only will you have a condition like RS is equal to RL, but you'll also have the reactance, which is the imaginary portions of the impedance. And in that case, they actually need to cancel each other out. So not to get too far ahead of things, but in an impedance matching network, you would need your load impedance to be the conjugate of the Thevenin source impedance, which may not mean anything to you yet, but by the time we finish this class, it will. Carter.
Where is RL squared installed?
Do what?
For some reason, I don't, try to see that negative R,
RL squared minus 2 RL squared gives me minus 1 RL squared. Yep. Okay, so anyone else care to look at the math? And 99.99% sure I did it right because I know I got the right result at the end. Any other questions about this before we move on ever so slightly? Yes, sir.
does it also be able to be,
How are we going to ever have a negative resistance? We're not. So I'm still okay with this. I mean, that is, yeah, I mean, technically speaking, we would need to put a plus or minus, but since we can't get negative resistors, we're okay. Okay, so if I plug this result into my power equation up here, right? So I know that PL was equal to VS squared RL over RS plus RL squared. Maximum power occurs when RL is equal to RS. So I'm going to have VS squared times RS over RS plus RS squared. That's the same thing as VS squared times RS over 4RS squared, or VS squared over RS times a factor of 1/4. Anybody got any beef with this? So if I had a practical current source, let me just make a note here. What do you think I would need to do? VS is equal to IS times RS. Literally just substitute it in. So that would be IS RS quantity squared times RS over, I'm just going to write this as twice RS squared. And so we can see that we're going to wind up getting a factor of 1/4 IS squared RS. So that is the expression for the maximum power that can be supplied by a practical voltage source on top, and the maximum power that can be supplied by a practical current source on bottom. Okay. So in your homeworks, on your exams, even out in your career, you may be asked to determine what the maximum power a particular network can deliver to a given load is, right? So to put things in context, let's say that you're designing a circuit or something like that, maybe an amplifier circuit, okay? So you've designed this amplifier and you want to make sure that the amplifier isn't pushing so much power that it would blow out your speaker or something like that. You need to figure out what the maximum power your amplifier can provide so that you know what size or what power rating of speaker to connect to your system, right? This is that relationship where the expectation is that you have been able to reduce your amplifier down into a practical voltage source or practical current source relationship using source transformation techniques, or much more likely, as we'll learn on Wednesday, Thevenin and Norton equivalent circuit techniques. But the same thing applies here, okay? So let's say that we have the following circuit. I'm intentionally making this guy fairly straightforward since I've been at this for an hour. So this is the circuit that we're given, and I want to know, A, what value of RL causes the remainder of the circuit to deliver maximum power, and B, what is the maximum power that can be delivered. So if you were posed a question like this, or better, when you were posed a question like this in your homework, your ICA, your exams, etc., effectively what I am asking you to do is to figure out, without changing RL at all, how to reduce the remainder of the circuit down into either a practical voltage source representation or a practical current source representation. Because we know that maximum power transfer occurs when RL is equal to RS, our source resistance. So if we can simplify everything but RL down into a single practical voltage source or a single practical current source, then the answer is in that final result. And then lastly, having our external circuitry reduced down to that level allows us to just use the maximum power transfer theorem in order to calculate that power very easily. So how would we convert this network up here into a single practical source connected to resistor RL? So turn the practical current source on the right-hand side into a practical voltage source, which puts everything in series. Then we could just do resistor combinations and voltage source combinations and be done. So 2 steps essentially. So what's 8 ohms in parallel with 0.3 amps going to look like? 2.4 volts in series with 8 ohms, right? You're ahead of me, Matthew. It's all right. So these 2 voltage sources are of opposite polarity, so they would subtract. So 12.6, I believe, is what you said. And then 3 ohms and 8 ohms are now in series. So this would look like 12.6 volts in series with 11 ohms in series with our load resistor RL. So to answer part A, what value must RL have for maximum power transfer to occur? Why is it taking you so long? 11 ohms. It's the only resistor that's left. To answer part B, we just plug in our results, right? So this is a practical voltage source. So we would have 1/4 of 12.6 volts squared divided by 11 ohms. So when I throw that into my calculator, I get a syntax error. Hold on. 3.608 and some change watts. So sometimes, and I believe in the second in-class assignment problem, you'll get to a practical current source representation more easily than you'll get to a practical voltage source representation. Your goal is to just get to a practical source, a single practical source connected to a single load resistor. Whether it's a voltage source or a current source will be entirely dependent on how you choose to analyze the circuit. All right. So unless anybody has any questions, you've got the better part of 45 minutes to work on that second ICA problem.